Welcome back to Calculus. In this video, I want to do a more complicated example. We've seen some simple ones, but sometimes optimization is hard, and I don't want to give you the impression that it's easy. So a couple things making this hard. One will be that the equation we have to the equation for the derivative is pretty complicated, the objective function. And the other is that we're going to have some constants in there that are letters that we don't know their values. And you can still do optimization in this case. It just means your answer is going to depend on those unknown parameters. So what's our problem? I want to find the area of the largest rectangle that we can describe in the ellipse. Okay, so remember this is the standard equation for the ellipse. Basically, A controls how much we stretch in the x direction, and B controls how much we stretch in the y direction. So let me remind you how ellipses work. I guess I can draw an oval here. Yeah, let's draw an oval. So we've got an ellipse, and now this is centered at the origin because the x and the y squared don't have anything added or subtracted from them. And, well, I guess I could draw a better axis than that. And how this works is normally I think that you start with the unit circle, and the unit circle would just be x squared plus y squared equals 1. And the a squared in the denominator stretches everything by a factor of a. So instead of going out to 1 on the left and right, we're going out a distance of a, so this will be a comma 0, and instead of going up and down by 1, in the unit circle we'll go up and down by a factor of b. So this will be 0 comma b. Oops. Okay, so you don't really need to know that much about ellipses to do this problem, but it doesn't hurt to have a little review. Now we want to inscribe a rectangle. So an inscribed rectangle means that the rectangle fits inside the ellipse and the corners are on the ellipse. And I guess I'm just going to assume, it seems pretty reasonable, but I'm going to assume that the rectangle has its sides parallel to the x-axis and the y-axis. Now, I'm pretty sure that's true. So we want a rectangle, something like this. I guess theoretically you could have some sort of slanted rectangle, but I can't imagine that would actually be the optimal one. So let's just go with this. Now, that looks good, right? I've got a rectangle and an ellipse. I kind of tried to draw the optimal one, but maybe that's not it. Maybe my corners should be here and here, and here and here, and that would make a bigger area somehow. I don't want to muck up the picture, but imagine you drew the lines for that rectangle. Maybe that area is bigger. So that's what we're trying to figure out, is where do you put these corners to make the rectangle as big as possible. Okay, we want the area and largest rectangle. So what are we going to do? Well, first we have this process, right? And first we need to name our variables. So I'm going to label this point right up here, x comma y. There are multiple ways you could set up the problem. You could give variables for the length and height of the rectangle, for example. I'm not going to do that. I'm going to use my variables as x and y because I want to use the constraint equation more easily, and that's going to be the equation for the ellipse. So my objective, actually, I'm going to specify a little more. So I'm going to write a sentence. I'm going to say let x, y be the corner, and I'll just let it be implied that I mean corner of the rectangle, but specifically in the first quadrant. There are four corners, and in general, any of them could be labeled as x and y, because x and y can be positive or negative, right? But I want mine to be the one in the first quadrant. And I get to pick, right? I get to name x and y whatever I want, so I'm going to call them this. Now, what are the objective and the constraint? That is the next step. Well, I'm trying to find the largest area. So my objective function is going to be the area for the rectangle. And unfortunately, it's not just x times y. X times y would be that rectangle right there area, but I do have 4 of those. So really my height is 2y and my width is 2x. So the area is 2x times 2y, which of course we can simplify to just be 4xy. Okay, so I've got the function I'm trying to optimize, but now notice this depends on multiple variables, x and y. So I need a constraint, at least one constraint, so I can reduce this to a function of one variable. And my constraint was already given to me. It is the fact that the point xy has to be on the ellipse. That's what inscribed means. So the xy has to satisfy the ellipse equation. X squared over a squared plus y squared over b squared equals 1. Okay. And while we're at it, I'm going to put a couple extra constraints. Because x is in the first quadrant, I know that x has to be in the interval from 0 to a. And y has to be in the interval from 0 to b. So I could write those with inequalities, 0 less than or equal to x less than or equal to a, 0 less than or equal to y less than or equal to b. But I like to write it like this so it's clear that I'm dealing with a closed bounded interval, which means when it comes time to check my critical points, I can just plug into the function instead of trying to like take a second derivative and verify that something's a local max and that gives a global max by the useful. I don't have to do any of that because I have the useful theorem, or because I have the extreme value theorem. Okay, so what's next? Oh, right, solve the constraint for one of the variables and plug in so that I can make a only involve one variable. So this is where it starts to get a little tricky with the algebra. I'm going to solve my constraint for y. So let's solve the constraint for y. So I'm going to subtract the x squared over a squared term. I'm going to multiply it by b squared. And then I'm going to take a square root of both sides. So normally when you take a square root, you need to put in a plus or minus. But I'm not dealing with y equals negative something. That would be the point at the bottom of the ellipse. And that is a point on the ellipse. But I specified that y was in the first quadrant, so I don't need the square root. So I take the square root of b squared, and I just get b. And then I take the square root of the other part, and I get square root 1 minus x squared over a squared. Please don't think that's 1 minus x over a. Square roots don't work that way. If you're subtracting inside, you can't square root each one separately. So this is as simple as it's going to get. Okay, so now I want to plug this into my constraint. So that tells me a, and now it's really just a of x, is 4 times x times y, but I want to use this big messy thing for y because it only involves x. And these constants, but remember, a and b are constants, so we're not treating them as variables. So I get b times the square root 1 minus x squared over a squared. Now that is the function I actually need to optimize. Okay, my function only depends on one variable and two constants, but only one variable. So I can take the derivative, set it equal to 0. All right, so a prime of x. Well, the 4b can just sit out there in front. That's just a constant. And now I have x times some square root stuff. That's a product rule. Right, so my first function is x, my second function is the square root. So let's do that. The derivative of x is 1, so derivative of the first is 1 times the second plus the first times the derivative of the second. And now I need to differentiate the square root of 1 minus x squared over a squared. That is a chain rule. So I take the derivative of the square root, I get 1 over 2 times the square root. That comes from the power rule, so if you don't believe me on that part, just write out what it would look like with the power rule and simplify it to this. And then we have to differentiate the inside function. So the 1 goes away, and we really have to differentiate x squared over a squared. Please do not use the quotient rule on this. This is a horrible time to use the quotient rule because this problem is already really complicated. We don't need the quotient rule making it even worse. Instead, you should just use the power rule, recognizing that 1 over a squared is a constant. So we just have that constant times x squared. So we're going to have negative 2x times the constant 1 over a squared, which means divided by a squared. Okay, so the constant stays there, you differentiate the x part. All right, so now I want to set this equal to 0 and try to solve. Well, I guess I better simplify first, right? Oh, sorry, that's not actually minus, that's times negative. So that's times there. Well, the first thing I can do, divide both sides by 4b, so that 4b can just go away, because 0 over 4b is still 0. And I can cancel a 2 from the top and bottom here. So let's just write out what that gives us, and maybe combine my x and negative x into an x squared. So I have square root 1 minus x squared over a squared minus, so I'm taking that minus sign out and making it subtraction. Then I have x squared over a squared in the numerator divided by square root 1 minus x squared over a squared. That equals 0. Okay, well, it still looks pretty messy, but not as bad as it was. So now I kind of want to combine those square roots somehow. So what you definitely don't want to do is like square both sides or something. That would be a horrible idea because then you'll still have square roots, but you'll have even more terms. Instead, I'm going to add my stuff I'm going to add the negative term to the other side. So we've got the square root. I'm going to leave this term alone. But then my other term I'm going to add to the other side to make it positive. X squared over a squared on top divided by square root 1 minus x squared over a squared. Okay, now I'm going to take my denominator here and I'm going to multiply it to the left. And because that's the same, I'm just squaring a square root, so the square root goes away. So I get 1 minus x squared over a squared equals x squared over a squared. Wonderful. Now I can take this term and add it to the other side. So we're going to get 1 equals 2 of those. And then I'm solving for x, so I'm going to get the x by itself by multiplying by a squared over 2. So I have a squared over 2 equals x squared. And finally, I can take a square root. So we get x equals the square root of a squared is a, divided by the square root of 2, which is root 2. Now again, I might need a plus or minus or something here, but I don't, right? Because I know a is positive and I know x is positive. So that's my x. That is my critical point. I guess technically, the derivative is undefined. If I look at this term up here, the derivative is undefined when x equals a, because then x squared over a squared is 1 and you have a 0 in the denominator. But I was already going to check x equals a anyways because it's an endpoint, so let's not worry about that too much. This is the only critical point kind of in the middle of the interval. All right, so we're moving right along. Now, how do we do this? How do we optimize a function? Well, let me write a of x again. So what was a of x? It was 4b times x times the square root of 1 minus x squared over a squared. Okay, so that was the function we're trying to optimize. And the possible locations, remember with the extreme value theorem, if you have x on a closed bounded interval, then we just need to plug in the endpoints and the critical points and see which one is the biggest. So the possible locations, we make a list of all the possible locations of the max. And that's x equals 0. Seems like that wouldn't be a good idea because, well, the area is going to be 0, but well, it still counts as a possibility. That's actually where you have the minimum area, right? And then x equals a over root 2, and x equals a. Okay, so how's this going to work? Well, I have to plug them all in. You cannot just get a single critical point and assume that that's the one you want. That is so bad. Do not ever, ever do that. Instead, you have to verify that the critical point is the type that you want. So we find a of 0. Well, that's 4 times b times 0 times 1. So that's going to be 0. Let's do a of little a. So that's going to be 4 times x, which is a, times b, times the square root of 1 minus a squared over a squared. Oh, but a squared over a squared is 1, so that part becomes 0, and the whole thing is 0. That shouldn't really be surprising. Those two things correspond to a rectangle that looks like this, where it doesn't have any width, or a rectangle like this that doesn't have any height. So those are actually minimizing the area. We want to maximize the area, so it's almost certainly going to be the one in the middle. Let's just check what it is because we want to actually find this maximal area anyways. So we plug it in, we get 4b times a over root 2 times the square root of 1 minus a over, well, I actually know what x squared is, right? I already found x squared. It's a squared over 2, so we'll just do a squared over 2 over a squared. And that's not looking so bad. Maybe we'll clean it up a little bit so I can multiply by root 2 over root 2 to rationalize the denominator. And then the 2 is going to cancel with the 4 to make a 2. So we get 2 root 2 ab times the square root of 1 minus the a squareds will cancel, and we just get 1 minus a half. So we get 2 root 2 ab times the square root of a half, but that's root 2 over 2, or 1 over root 2. Then the root 2's can cancel, and we get 2ab. Not so bad, right? And note that that is positive, which is greater than 0. So the max area is 2ab. And that's the answer to the question. The question is actually, what's the maximum area? But it occurs at when the corner is xy equals, so what was that first one? A over root 2. And then what do we think the y coordinate is? Well, we solved for y somewhere up here, right? There's my y. So what if I put in x equals a over root 2? Or sorry, yeah, a over root 2. Or let's say if x squared equals a squared over 2, then y is going to be b times the square root of 1 minus, the a squareds are going to cancel, just like before, so 1 minus a half. So that is b. 1 minus a half is root 2, or sorry, is 1 half. So the square root of a half is b over root 2. So y is b over root 2, x is a over root 2. Hey, it's even got some symmetry like it should. Okay, so wonderful, wonderful. I guess we could have found that first and then just multiplied the x times y to get the area. But, well, same way either way, right? Okay, so that is maybe enough for that. Notice that our answer does have a and b in it. Notice that I checked that my critical point actually did what I wanted. You have to do that every time. It's very, very important. Okay, but with that, I think we'll be done. We'll do some more complicated examples in the next video, and I will see you then.